Hello viewers, today we are taking up next topic, that is frequency response of operational amplifiers. Up till now we have talked of introduction to differential amplifiers, various configurations, operational amplifiers, its open loop and closed loop configurations, voltage series and voltage shunt feedback configuration. Now we will be talking of frequency response. So the resources used are shown in this slide. So up to now in all these discussions we have treated the gain of OpAmp as a constant quantity. However, it is a complex number that is a function of frequency. Therefore, at a given frequency, the gain will have a specific magnitude as well as a phase angle. This means that the variation in operating frequency will cause the variation in gain magnitude and its phase angle. The manner in which the gain of OpAmp responds to different frequencies is called the frequency response. A graph of the magnitude of gain versus frequency is called the frequency response plot. This plot is included on the data sheets of most OpAmps. Although gain magnitude may be expressed either in decibels or as a numerical value, the frequency is always plotted on the logarithmic scale. Remember that to accommodate large frequency ranges, the frequency is assigned a logarithmic scale as the gain magnitude is assigned a linear scale and expressed in decibels to accommodate very high gain of the order of 10 raised to the power 5 or higher. The frequency response of amplifier is obtained from the experimental results by measuring its input and output voltages at different frequencies. Another technique used in the AC analysis of networks is Bode plot, composed of the magnitude versus frequency and phase angle versus frequency plot. In magnitude versus frequency plots, the magnitude is always taken in decibels, although both frequency response and Bode plots indicate the effect of frequency variation on gain. The Bode plot is generally used for stability determination and network design. So compensating networks. Generally for an amplifier, As the operating frequency increases, two effects become more evident. The first one is the gain magnitude of amplifier decreases and the phase shift between output and input signal increases. In case of an op-amp, the change in gain and phase shift as a function of frequency is attributed to internally integrated capacitors as well as stray capacitances. These capacitances are due to the physical characteristics of the semiconductor devices, BJTs and FETs, and the internal construction of the op-amps. The manner in which the gain of op-amp changes with variation in frequency is known as the magnitude plot, and the manner in which the phase shift changes with variation in frequency is known as the phase angle plot. Generally, manufacturers supply magnitude plot for the op-amps they produce. However, phase angle plots are not generally provided, especially for the later generation of op-amps such as 741, 351 and 771. This is because phase shift of these op-amps are less than 90 degree even at crossover frequencies. Recall that crossover frequency, also referred to as unity gain bandwidth, and it is the maximum usable frequency for a given op-amp. For example, in the case of a typical 741 op-amp, UGB is 1 megahertz. The rate of change of gain as well as the phase shift of an op-amp can be changed by using specific components with it. The most commonly used components are resistors and capacitors. The network formed by such components and used for modifying the rate of change of gain and the phase shift is called a compensating network. So the network which is formed by components such as resistances and capacitances which are responsible for modifying the rate of change of gain and phase shift, that is rate of change of gain and phase shift is changed by the compensating networks. The phase lag and the phase lead are most commonly used compensating networks in op-amps. These two networks are indicative of their functions since phase lag contributes a negative phase angle and phase lead a positive phase angle. Thus, the main purpose of a compensating network is to modify the performance of an op-amp circuit over the desired frequency range by controlling its gain and phase shift. The first generation of OpAmps, such as 709, requires external compensating networks, whereas later generation of OpAmps such as 741 and 351 have internal compensating networks. Therefore, there are two types of OpAmps. One are internally compensated and another are externally compensated OpAmps. In internally compensated OpAmps, the compensating network is designed into the circuit to control the gain and the phase shift of the OpAmp. On the other hand, external discrete compensating components, that is resistors and or capacitors, are added at designated terminals in a non-compensated op-amps. For the proper operation, the manufacturer recommends appropriate compensating components for uncompensated. So figure A shows the frequency response of an internally compensated OpAmp 741C. So on the x-axis, it's the frequency variable, which is logarithmic scale, and on the y-axis, it's the open loop gain in decibels. We can see, as already discussed, the breakaway frequency of this 741 is 5 Hz, and at 1 megahertz, which is the UGB, the gain is 1. So that is the reason we have taken this x-axis as a logarithmic scale, because we want a lot of frequencies to be displayed on a single graph. So figure C is the frequency compensation circuit for mu 709. So we are using here R2 as 15 ohm when the amplifier is operated with capacitive loading. So figure B shows the frequency response of non-compensated network OpAmp mu 709 for various values of C1, R1 and C2, which are shown in figure C. So for various values of C1, R1 and C2, we are able to have different curves. So this is also x-axis is frequency and y-axis is open loop gain, and this is for 709, which is externally compensated or non-compensated OpAmp. So we can use as per our requirement. So the 741 is internally compensated and 709 is non-compensated OpAmp. The open loop frequency response curves of these OpAmps as well as the connection diagram are shown in the figure above. So 709 requires 3 compensating components, a resistor and 2 capacitors. You can see the nature of frequency response for 709C depends on the value of compensating components used. On the other hand, 741C OpAmp has internal compensation capacitor of 30 picofarad. So next class we will be talking of frequency response of these internally compensated as well as non-compensated or externally compensated OpAmps.